So in my talk today, I'm going to talk about high-dimensional optimal transport. That's very hot off the press. Not all is very well digested, but I erred on the side of excitement because this is some work we've been doing that has opened up many new avenues. I will say though, so I've worked on medical imaging at some point in my life. I've worked on deep neural networks for the more recent time of my life. I have not really been able too much to connect these two worlds yet. So if you really want to talk about something with deep learning with medical applications, this is maybe a little bit far away, but it's a new tool that we have here. But one of my students, Derek Onken, is going to actually have a poster later on doing some exciting work in applying PDE-based neural networks to classification. So you should stop by this poster then. Anyway, so I have a packed agenda. I want to kind of slowly talk about optimal transport. I'm not sure everyone has seen it, but looking at the schedule, I think this will be one problem that will come up every now and then. We already heard the word Wasserstein-Gahn, so that has some connection to OT. And I want to start basically following kind of my career with a low-dimensional OT. So that means you want to match densities in low dimension. And for me, I define low everything less or equal to 3. Okay. And I want to show you some work that we've done back then in what's called image registration that have actually then fueled the new work that we've done last semester. So then there will be sharp discontinuity to going to high-dimensional OT. If you think about matching densities in a high-dimensional space, I probably need to motivate you because I cannot show you images of in 10-dimensional space. We don't have CT or MRI or PET or anything. So my angle will be generative modeling because that is one technique in machine learning that is working with high-dimensional data set. And I think as a technology, if we can make it work, would actually be very nice in many respects for medical applications. And then it'll become more technical. So there are 3 options how to solve an OT problem. And we will formulate it as an even more general animal, which is called a mean field game. So one special case of a mean field game is this OT problem. So I go through all 3 of them because then what we've done over the last semester is to kind of take a look at these 3 options. So one is solve a variational problem, one is solving a whole bunch of optimization problems individually, and one is solving a very high-dimensional PDE. Okay, so all of them have pros and cons, and I think what we've tried to do is to take the pros of all these 3 and put them into one package and forget about the cons. So that's something we're still basically still working on, still interested in. But I'm going to show you a few experiments that we already have that show that this can actually work surprisingly well. And that part then, of course, will also involve a neural network. So if you wait for the neural network to come, I mean, it'll hit us halfway through. Okay, but before getting started, maybe some really older slides from my PhD. So here's a problem from medical imaging. It's a PET image, and it's a PET image that is gated because you realize that in PET they use it a lot for cardiac applications. They basically measure metabolism in the body. And in order to do so, you take an acquisition of a few minutes. So you see the heart, it's the left ventricle that you see here, is moving up and down, and it's contracting. And that is a problem for imaging, because then you get a blurred image. It's like if you took an image with your iPhone on a dance floor, and someone is moving very quickly, you have a blurred image. So in here, what's special, though, is that PET is a density mapping. So if you think about the following idea, let's take all these frames, move them, shift them around. So basically, we estimate the motion and undo it. Then you want to be careful that you are not changing the amount of tracer or the amount of density that is in the images. So that is one thing that we have studied back then. And we've studied this as what's called an image registration problem. So you have a reference image and a template image. I think in the previous talk we also talked about normalization. So registration is very much used for that. You want to align these 2 images like so. so that the template, when you kind of rotate it and maybe do some other nonlinear stuff to it, looks kind of similar to the reference image. You can phrase it as an optimization problem. So you have a measure that tells you how well this matches that. You have a regularizer. And then most importantly, you have a PDE here that is telling you how exactly to transform an image. You can choose, there are two options. You can have this equation here that's also related to the optical flow. It's a transport equation. It'll preserve the intensity of the images as you move it, but it will not, for example, preserve all the mass. So for today, we are much more interested in this kind of constraint. It's a continuity equation, okay? But and that then leads to also optimal transport, because you could think about this image as a density that you want to transport to map another density. Okay, it's a dynamic reformulation of optimal transport if you are kind of from the area. There are different options. So I'm a mostly numerical optimization guy. So there are a couple of things that if I pose this problem to you, that you need to go through. So one is you need to see that what do you minimize over. So there's a v and there's a u. V is a velocity, tells you like how stuff is moving in this transport problem, and the U is the density. Okay, so one idea could be, let's eliminate this constraint. After all, we can always solve this PDE if we have an initial condition and we have a velocity. Okay, that way we could get the U at time 1, and we can just deal with this objective function. Okay. That's the angle I want to do, because that's also what we do a lot in the machine learning world. So if we want to eliminate this PDE constraint, you realize it's a hyperbolic PDE. There are a few things that can go wrong. And you could, for example, think about something called a Eulerian method. That means that you discretize in time, and you have a fixed grid in space. So basically all the pixels kind of just see what is the density that moves by the pixels. The pixels themselves don't move. And there's a lot of nice work, including from Stan, that talks about how you can do this in an explicit way, because explicit is nice to differentiate. But there is one problem, or one catch with that, is you will have to have very small time steps. If you have taken a numerical PDE class with hyperbolic PDEs, you know that there is something like a CFL condition. So the problem becomes relatively big quite quickly, and you remember maybe the CFL condition also has a velocity in there. And that is the guy you want to optimize, so you're stuck with being very conservative and slow, or being very optimistic, and stuff may actually completely break, unless you go to some of these fancy schemes. Then there is something called a Lagrangian method, and the Lagrangian method is what I'm going to motivate that we should be using here, and that relates to the method of characteristics. Hyperbolic PDEs evolve along characteristic lines. If you follow them, if you can trace them, so to say, you know how stuff is moving. Okay, and then you basically have that option. The nice thing is they are always stable. Unconditionally stable, in the sense that you can pick any time step. So we are going to put that in our basket. There's an interpretation to this, so you can think about the stuff from here being, we're here in the continuity equation, we have stuff in here, we move the mass from here to this location, and then we need to figure out how to split the mass. So that's a scheme, and this path is dictated by the velocity. Okay. So I'm going to skip. It's just a little demo of how this works, and it actually does. And you could use it to solve this registration problem. So you can see, you have reference images, you have template images. So this you want to deform to match to this, and there are now a couple of options to do this. So in that project, we did it like 2017, I think, was the first time we did this with Lagrangian methods. There are two takeaways that informed what happened last semester. And one thing was that eliminating the PDE constraint with the Lagrangian method is actually really nice, because it's unconditionally unstable, it was very memory efficient, and actually very fast. One big thing that we still didn't figure out was the part, so you trace a particle, and then you are typically, we are in images, not in the center of a pixel or of a voxel. So you need to figure out how to split the mass among the neighbors. And if we think about solving this in a high-dimensional space, there's something called a curse-of-dimensionality, which means that basically in a high-dimensional space, we're not allowed to have a grid. Okay? So that was one thing we did. We did much more. We are going to do, but much better in a little bit. But other than that, that was really a foundational thing here for us. So if we think about high-dimensional OT, that is something, again, hard to motivate maybe from an imaging perspective, because there are images in 2 and 3 dimensions. I would say, we understand the problems very well. There's no need to do too much work. But there's one problem that popped up in the machine learning like in the machine learning literature, that really motivated us to go back to what we've already learned about registration problems. And that is called normalizing flows. So normalizing flows is a kind of a funny name we need to parse. I believe it's called that way because you think about this distribution here. There's a nice distribution, and there's a normal distribution. And you think about this distribution up here. So that is a more interesting distribution. Completely not a normal distribution. But think about in practice, the space of all medical images is probably not going to be normally distributed. If I sample from it, it doesn't look like a medical image. So it is one that probably has multiple modes and all that kind of stuff. So the idea in a normalizing flow is, can I find a transport plan between this nice density that I can easily sample from and this complicated density that I'm interested in? So in this case, that's denoted here by these lines. And if you can find such a mapping, the amazing thing is that now I can sample basically and I can sample in a statistically correct way from this complicated distribution. How I do this, I sample in here, and then I push forward the sample to wherever I'm ending up over here. Okay? So that is one goal. Of course, I'm doing a little bit of a crime here. I told you I want to motivate this in high dimensions, and I show you a one-dimensional picture. Okay? Make the transition now to go from this to a high dimensional space. So normal distributions we can sample from in any dimension, and if you have other data sets in a high dimensional space, then you can try. Of course, that is now the main crux, is how do you find this mapping? And that is not going to be too easy. But there have been a number of works actually recently along this direction that are quite nice and quite promising. In the beginning, actually, there was no notion of what kind of mapping you're looking for. Any mapping. And most machine learning papers still say, well, find me any mapping between this density and that density. In the field of optimal transport, which is one heavily studied problem in applied math, we know that if you assign some transport costs. So you say, I want to map these densities, but I want to find the one mapping that minimizes the cost with respect to, I don't know, the L2 norm or L1 norm or whatever. You gain regularity. So there are a couple of really interesting papers recently that connected optimal transport actually to these normalizing flows in generative modeling. And that is pretty much also what we want to do here. If you do this though, so the PDE that governs this path here is still going to be the continuity equation. So we are going to have to solve this in a high dimensional space and to kind of avoid the curse of dimensionality. That's going to be the main problem in this business. So what we've done here is let's go a little bit lightly through the theory. We formulate the optimal transport problem as a mean field game. So there's a lot of letter soup here. So we phrase OT as an MFG, and that kind of leads us to something called a Hamilton-Jacobi-Bellman equation. So in the end of the day, unfortunately there is no shortcut. We've tried to take as many shortcuts as we like, but using these insights from the theory, putting that into the machine learning framework really helped us in getting results. So But I will cut corners here. And so this work, especially like all the heavy theory stuff, I'm definitely not the main guy doing this. It would not have been possible with I think anyone in this team. We could not have done it without any of them. And of course, special thanks really to the IPAM staff and the organizers from last semester, because being here actually really helped us a lot to get this off the ground. Okay, so optimal mass transport. Here's one example I'm going to use. So I have some density here. You may see, a few dots, shining through. They're a little bit, they're not so easy to see here, because the mass is going to be the same as the one in here. So that's going to basically push together everything to the center. And what I'm going to do is I want to find the velocity that makes row 0 and row 1 the same, like at both ends of the time domain. And I'm going to use a quadratic penalty for how much stuff is moving. So that's basically motivated by, if you have a lot of density in a point and you move it very far, you're going to pay a price. Okay? And that's important, because that'll help us in the theory and the practice. And this is one result I think we can do better by now, but it's kind of to give you a feeling. So these guys are all pushed into the middle, and they visually kind of are supposed to match approximately. So we do something called this, I would call suboptimal transport. We want to do roughly like optimal transport, but maybe not so serious. Okay, so mean field game, I don't want to give you like the whole story of it, but there is a way to formulate many problems that have a continuity equation as a constraint, as something called a mean field game. And they have been used in economics and data science and in many other areas. The way this is typically working is, so you have the constraint, you start with row 0, that's say your input image. You want to evolve in terms of the continuity equation, and then you have 3 different kinds of costs. So one is called L. That's going to be the transport costs. So think about this as just being norm v squared. Okay. One is called F here. That is a cost that you can use, for example, to model congestion, or you can model it so that you avoid the agents in this game avoid certain regions, or avoid each other, or like each other, attract each other. These are terms that depend a lot on the density. And then you have something called a G that is going to be a terminal cost. So we can simplify here for our case. We can drop the F, and we make this a norm v squared. And the G here will roughly measure how well does rho at time 1 match the target. And then you kind of can formulate like optimal transport, but you can also have interesting things. So here, for example, it's a kind of one computed example that we have. So we have a normal distribution, we have a Gaussian mixture, I think, and we try to get everyone over from here to there, but we try to make them avoid this black region here. Okay, so that would be an example where we use this F term here to say, hey, if you go through the center of the domain, you're paying a huge price. Okay, you can still go. We don't prohibit you from doing it, but if you can make your way around it, then that's what you do. This would not happen in optimal transport, though. And by the way, these lines here, you can also think about them as the characteristics. So, there's that. Yeah, and in this framework, there's a lot of beautiful theory that I've studied here last semester, yeah, it's a very general framework, but for today, really, OT is everything. There's another way, actually, to look at this problem, because in this, so this is a variation of formulation of it, where you try to find the velocity. You think almost like a central planner. You have a central guy that says how everyone is going to move. But you can equivalently, in many cases, also make this an agent-based model. So you can flip the coin, and you can say, each agent, you describe it by x, its position, and t is the current time, just tries to optimize its objective. Okay? So now you forget about the big picture, about the central guy figuring out all the velocities. You just find each agent, and each agent optimizes something. It's an equivalent way in the way we set up the problem. If you want to do this, then each of these agents solves for its velocity. There is the characteristics equation here popping through. So the the state of that agent is going to evolve like the velocity. You start at x and at time 0, and then you evolve basically based on this velocity. And think about everyone can optimize that. If you want to do this, so what is nice about it? What's nice about it is that the computation kind of decouples. Think about you have a whole bunch of agents. They all solve their problem, and that you probably can parallelize that whole process. If you think about the variation problem, you have more like a macroscopic view. So you kind of need to, it's nice because you can abstract from the number of agents. It's like a limit that you take, but it's more coupled. So we want to combine these two things. In any respect, so in here, an important quantity is called this value function phi. So if you think about an agent that is at x at time t, and it finds the optimal velocity, that will give him a cost or a value. That we denote by phi of x comma t. So that is kind of the minimal cost it takes me to optimize my trajectory. Okay. There is something called the Hamilton-Jacobi-Bellman equation. For those of you that have seen it, they probably think it's, of course it pops up. I had not seen it before, but that links, so to say, the macroscopic and microscopic view, and can also be seen as in some simplified sense as the optimality conditions of the variation problem. So what do they say? So the HJB equation is basically, in this case, like a Burgers type equation. I put a minus partial t here because the time counts backward, and you have a final time condition. The final time condition depends on this term g, which was the terminal cost. The right-hand side here is going to be 0 in our case, fortunately. And then you really recover like a Burger type equation. And the variable here is this phi. So that's a value function. And the one important observation is that if you have the phi in this kind of problem, again, that's a value, or the cost it takes an agent to go from xt to the final state. If you have that, you can recover the velocity. It's minus the gradient of that function. So there's a little bit of calculus that we went through. But what that tells you is that you can either optimize for v, or you can optimize for minus grad phi. And that is something that we try to exploit in our approach, because then the phi here just is a scalar function. We know that the solution to the problem will be a gradient of a scalar function. If we just optimized over any velocity, that may or may not be true. So it kind of reduces the dimensionality slightly, not so significantly, but mostly working on the grad phi is kind of one way to make sure that you have something that is matching the physics or whatever you want to call it. So now that you have three options. So you can solve the variational problem, either for v, or I would recommend for grad phi. You could, for every agent, you could solve the individual problems with v or minus grad phi, or you could solve this system here of PDEs. So they are coupled, because here's a grad phi, here's a phi. This one goes forward in time, this one goes backward in time. So solving these two PDEs is an option. You can recover the solution from it, but it is not going to be cheap. Because if we think about the dimensionality here, then this is going to be in a space that depends on the dimensionality of your data. So if you give me densities in 2 dimensions, 3 dimensions, okay, it's a 3-dimensional PDE. If you give me a data set of CT images, that's going to be a 512 cube dimensionality of a PDE. Okay, so that is going to be so they all have pros and cons. So here's what we do. We take a variational problem, okay, that's something we like. Then we still need to talk about how do we solve the PDE, the continuity equation. So that's this guy in a high dimensional space. For this, we use a Lagrangian PDE solver. So basically, as I showed you, we'd follow the characteristics somehow, and we find a way to estimate the density. That's nice because it doesn't require a mesh, and you can parallelize, and it's somewhat related to the microscopic view. Like for every particle in this, you can think about it as being one agent. Then comes the fun part. We take the phi and we parameterize it as a function with a neural network. That is mesh-free, and the rumor on the street is it's very efficient. We'll see about that and see how it goes. But what was really a crucial thing that we had to wrestle with is, so this phi here, I mean, it should minimize, it should solve the variation problem, but it should also adhere to these optimality conditions. So what we do in practice is we kind of penalize violations of these as like a soft penalty. So that kind of brings in a little bit of this global flavor of these HJBs, and it gives us regularity. For example, in OT, the characteristics should always be straight lines. If you make sure that in your solution you only have straight lines, guess what? You can actually simplify the numerics and run your code much faster. So that is what we do here. So that's where we kind of put together all these pieces of the puzzle. Okay, so that's going to be the rest of the talk. I will talk a little bit about these steps and show you some pretty pictures in the end. Okay, so the Lagrangian method, I think that was probably the easier part on this whole thing. So if we have a PDE like so it's a continuity equation, and I already now put in that V is equal to minus grad phi, because that makes a lot of sense to me, and it actually simplifies the numerics for us. So you go from row 0 as your initial. So if you look at this along the characteristics, so you go along Z, X, T, and T. So Z will be the characteristic. You can get it by integrating the negative grad phi. Then this equation here is true. So that's a calculus thing. I think Jacobi's identity or something like that. It's a very old kind of relation. But what this allows us to do is, if you ask me, so what is rho at z comma t? I can just say it's rho 0 of x, so where I started, divided by the Jacobi determinant. Okay. So that gives us a way, in a hopefully mesh-free way, to estimate the density. So what we did previously with, you push things forward and then you need a grid to divide the density, it's gone. So that was one realization that I think got us started here, that we don't even need to do this anymore. Catch here is, so how do you compute this? So that's the determinant of the Jacobian of z. Typically, you would think, it's a d cubed flobs. I mean, you build this thing as a matrix, compute the determinant. How bad can this be? But again, the d here will grow. So we wanted to be, you want to be a little bit conservative. And also in the normalizing flow business, what people typically do is they, instead of computing the determinant here, they use that you can get the log determinant by integrating, in our case, the Laplacian of phi along the characteristics. So how this in general goes is you take the trace of grad z. If you integrate that along the characteristics, you get the log determinant. And in our case, since z is the gradient of phi, and then the trace of the Hessian of something is the Laplacian, we get this I think, quite beautiful result that we can integrate that. Okay, great. So what does that buy us? We can solve the continuity equation. We can now, in the optimization, we can eliminate it. So we have an unconstrained problem. We get the density along the whole path. We have to still think about how to measure all these other costs, like how much we're moving, how fast we're moving, how far we're moving, the terminal cost. But in some sense, we have turned a PDE into an ODE, or a set of ODEs. And the nice thing is they don't talk to each other. If we start this at x or at y, we solve them separately if we are given the phi. So that's one crucial thing if you think about solving this in high dimensions without the mesh. Okay, now you collect everything, and this is the problem that we are solving. I still wrote it down as a constraint problem, but I want to say that this constraint is just an ODE. So you initialize it somehow, and then you keep integrating this part here to get the characteristics, this part to get the log determinant, this part to get the transport costs, and this part here to look at how do you violate the Hamilton-Jacobi-Bellman equations. Because also this we can all do in the moving coordinates. So we put that all together, and then we sum up a few things here in the objective. And really the way this goes is we have a current iterator phi. We compute all these things explicitly, no big magic, and then we treat it kind of as an unconstrained optimization problem. There are a few more things to talk about over this entire week, probably. So you have an expectation here. So because we are in high dimensional spaces, this integral that we had, the space integral, we need to talk about what to use there. The natural thing is to do some kind of a Monte Carlo idea. So we use, that's why we wrote it here as an expected value with respect to the density phi rho 0. And there are a lot of changes of variables that you run into because you follow the characteristics and you don't have a Eulerian perspective, but okay. And then in the end of the day, so you have a stochastic optimization problem. There are two ways to solve it. I'm going to show you what any machine learning person would recommend, like stochastic approximation schemes, SGD, ADAM. Not working so well for us, by the way, to spoil it. And then there's something called a sample average approximation, where you take a large batch of samples and then you apply the numerical optimization method of your choice, like a BFGS or Newton or whatever. It's working a little bit better. But again, this was a very sunny semester because there was no grid we needed and all the computation are embarrassingly parallel. Great. So probably at this point, so that was, by the way, probably the first 2 weeks of the whole thing. But I told you I spent a long semester here. Because if I wanted to tell a short story, I would say, okay, now you have this. It kind of looks like what people call these days neural ODEs. Okay, what do? I mean, you make phi a neural network. How hard can that be? And then the problem is solved. Because neural networks are universal approximators. The solutions here for the variation problem exist, so they should also be able to approximate that, and it's a done deal. So we thought. But actually it opened up much more of a discussion. Because now if you actually think about how to model the neural network, and there are already a few special assumptions that you have here, because we will use phi, but we will also use the gradient of phi, and we will also have to use the Laplacian of phi. And then we have to differentiate that whole stuff with respect to whatever weights we use to represent the neural net. So that's a little bit different from classifying images or something like that. Okay, so neural networks, just a little bit of a primer. I've worked on this a little bit. We've all seen these pictures. So you have input and output features. So in our case, say this would be like a 3-dimensional space, and this would be like the value of phi. And in our application, they're really ancient techniques, starting in the 50s, but they become slightly more popular. Let's understate that in the recent years. I'm a big fan of writing this not in pictures but in numerical or like in linear algebra notation. So basically, what a neural network is just a bunch of affine transformations, and then with some nonlinearities. That looks much more familiar to what we learn in numerical analysis. And these funny arrows here basically mean which feature talks to which other feature. You can see that or you can model it with the choice of the sparsity pattern here. Okay, so that's and there. One thing in terms of the diversity of neural networks, there's a whole zoo of models that you can choose from. What we chose here was something that I personally have worked on before. It's called a deep residual neural network. So in a very simple fashion, what this is that you have your features y, at the next time point are given by the old features plus and then some nonlinear update. So that's kind of was a recent innovation in 2016 or so. Because in the older neural networks they didn't have this. Actually, I found a paper by Yannis Kevrikitis from 1994 where they had some thing like that. So probably he has worked on ResNets before this name even existed. But in image processing, this has really been taking off. One nice thing is that you can actually turn now. So we have the high-dimensional, very HJB and variational problem, but even our solution approach also has some smell of a differential equation. If we realize that we should put in a small number h in here and take a limit and have then the network itself as a dynamical system, and that's stuff we've been doing over the last 2 or 3 years, and other groups as well, to use kind of these insights to model deep networks, to look, for example, at the hidden features as a video, and think about what kind of dynamics make sense. So, and in my work, and also in the work that we've been doing here with the optimal transport, using these differential equation-based solvers really gives us a little bit more of guidelines and more predictable pattern. I should say, that there are a bunch of things more than I can talk about now. So you can ask questions like, okay, is the network stable? You can make this a PDE perspective or so. I don't want to go into that because in this very room, I already gave a few talks last semester about these different things, and the videos are up online. But for the problem in the OT, so for the mean field game, what we choose is we choose this n here. Can be any of these above. You can put whatever neural network you want. It takes as an input s, which is actually x and t, so that's space and time, because it's a function that varies in both of these variables. It will have some weights. We chose to add also a quadratic in here, just because we like quadratics, and they, for example, allow you to express very simple shifts immediately without going through the fun of a neural network. Again, so this model you can pick whatever you want. I just want to make one quick explanation what we do here. So for the ResNet, what we do is we start basically we have m layers. So the first one will just be a normal single layer perceptron. This K0 here is one matrix that we're training. It can make the space bigger or smaller depending on how wide we want things to be. And then we go through forward in time. So you have the U1 is U0 plus H times this nonlinear transformation, and this is kind of this forward Euler method that comes through, like the ResNet. So it's a really simple architecture. If you ask me what is the gradient of this, you could ask Torch or whatever machine learning framework that is. But what you do is you just write these whole things upside down and take derivatives of everything. So it's just a chain rule here. We went actually through this whole exercise to compute the gradient of phi analytically, because then when it came to computing the Laplacian, so if you think about the Laplacian, which is kind of a trace of a Hessian, so to say, with backpropagation, if I wanted to code this, I would need d passes through this whole thing. And I haven't really, that's something I think my students will prove me wrong, but for me, it didn't seem like a very appealing thing to do. So what I sat down to do is to hand by hand compute this damn thing, and figured out that I can do this linearly in D. So basically with the same number of flops, but with the benefit of having only one pass through. So if you think about putting this on a GPU with dense operations, I'm hopeful that this will pass the test of time and still be faster. And you can do it. It's not so hard. Okay, so a few pictures. How would that work? So again, this is so far. Actually, one thing we realized is So we wanted to solve an OT problem in a high-dimensional space. Unfortunately, none of our friends in radiology could give us a 100-dimensional CT image. Okay? So we had to really to think hard about what could we even test. So what we chose to do is to do something silly, and I mean we have to get more serious. And actually, Derek and some other people are already working on using this for more interesting data sets. But what we chose here, so we have these 8 smaller Gaussians that we want to push into the middle, and we can formulate this problem in any dimension by just saying it's only the x1 and the x2 dimension that matter. The other ones we kind of say nothing happens. We don't tell the neural network that, but that's how we set up the problem. So that way we would anticipate that we would see more or less the same transport plan independent of what dimension we solve the problem in. If you have better ideas, please come talk to me, because that's the only thing I could do so far. Okay, so the way we set this up is that really we ignore all the other dimensions if I show you something bigger. We have a very simple optimization strategy. So we use BFGS. Not LBFGS, like really BFGS, because I'll show you that we can actually solve this kind of problem with very few parameters. We do 500 iterations. So this is an SAA approach. So you sample a large batch, and then you run with it. But in order to not overfit, we resample that batch every now and then. We have a very simple backtracking. It's a straightforward code, and of course we also have Adam as a comparison, just to see how that is doing. So here is one actually quite surprising thing for us. And the short story is that doing the right math actually pays off in the end. And it was not that we started out with this picture. So let me walk you through that. So you have again the initial and the target density. Then one question is, so I showed you this ODE that tracks the characteristics. How many, what solver should you use for this? How many time steps do you need? So what we did is we used an RK4 that has worked well for us in the medical imaging applications. But still you want to cut down the number of time steps. So we started with, say, 2 time steps. Okay, 2 time steps, and not worrying about this Hammond-Jacobi equation. And then you get kind of this kind of a result. And you see many things that we do not like. So first of all, this image is supposed to be similar to that image. Not so much. That image should be similar to this one. So by the way, so this is the push forward of this, and this is the pull back of that. So kind of we transfer it both ways, because in the end you need to both directions to sample and to match. So both of them are failures here, and then here you see these red lines. These are the characteristics. These are not optimal characteristics, because optimal characteristics are straight lines. So that actually, when we first time saw this, we thought, well, maybe this whole project is over, or we hit it harder with a little bit more math in this case. A natural way, by the way, we did already back then, is to say, okay, let's use more time steps. So we use 4 times as many time steps. Things start to improve. So this one looks almost similar. This one looks similar. The characteristics become straight, because we integrate the transport costs also with a higher accuracy. So if you have these detours, you will detect them and you will pay for it. So the optimization seems to work. But the magic thing happens when you put in this soft penalty on the HJBs, because there, with 2 time steps, and so pretty much the same cost of computing, you immediately get straight characteristics, which, by the way, for the picture are computed with more than 2 time steps, just to see if there is anything. So in this sense, I mean, both the quality was better and the compute was much, much cheaper. So we really liked to see that picture. So this is just what happens when you add dimensions. So 2 dimension, again, is not so interesting. 10 dimension, 50, and 100. And more or less, things stay as they are. Of course, you pay a higher price if you have more dimensions. The data becomes a little bit bigger, but also you need a few more samples to have a nice approximation of the integral. But the nice thing about Monte Carlo is The error estimates do not scale with dimension. It's, I mean, Monte Carlo converges slowly, but it converges slowly with the same slow rate in any dimension. Here you see the runtime go up, but it's not going up exponentially. And that was the whole deal. We wanted to avoid the curse of dimensionality, so exponential growth in cost. So yeah, here's if they are big fans of or experts in stochastic approximation schemes, come talk to me, because so far we haven't made them work. And by which I mean, so if you look at the conversions graphs so red is ADAM, which is a state-of-the-art tool for PDE-based neural networks and stuff like that. It did not perform for us very well, and especially it was not able to really match the optimality criterion, so the HJB. By all means, if you have any hints for me to improve this, I'm listening, because these schemes will be important for us moving forward. But so far, it's not so easy. Then here is a quick comparison with how well. I mean, I showed you some nice pictures, but maybe a question to ask is, so if I'm in 2 dimensions, I have plenty of options to solve this problem. How well do we compare to what against those schemes? So here is a Eulerian solver. So that is a very almost technology kind of approach. So you use this dynamical OT. I use the conservative finite volume method, which means that I'm not losing any mass on the discrete level. You end up with a convex optimization problem and not this horribly non-convex machine learning problem that I showed you. You can attack it with the Newton's method and solve it to a very high accuracy. So here's what you see in a side-by-side comparison. You see the Lagrangian and that's our approach, that's the Eulerian. So, I mean, they look similar, differences and similarities. The characteristics really look pretty much the same. And I would say like the suboptimality, so if I look at the final value of the objective function, is about 0.5% worse for the neural network. But we get there with fewer weights. So you can guess which number of parameters is for the finite volume and for the neural network part. Because here we have the philosophy to have really small neural networks. So we had like a 300 something weights, and then really kick it in the optimization. Yeah, we were able to do that here. Whereas, so I was actually kind of surprised that even in terms of complexity, these things surprised me, because I come more from this camp and not so much from the other camp. So it was really interesting. Yeah, to wrap up, we published our code. I think that's very important if we work in this area, to make things, I mean, at least do an effort to make everything as reproducible as possible, because the main result is actually exactly the implementation and the experiments that we achieved with it. So you can try it for yourself. We implemented it in Julia. That was just the quickest thing for us to do. And we already got 4 stars on GitHub. I expect more now after this talk. So it's really taking off. And yeah, to summarize, this, I mean, probably I've been talking way too quickly and so on. And there was a lot of things to digest. And there is a lot of things to digest. I just can't do anything about that, but to recommend to maybe look into this paper, where we tried to fill this a little bit more with substance. I think the main story is that if you're interested in these high-dimensional OT problems, and you want to attack them with neural networks, which is pretty much what we do these days, just doing it was only like maybe 50% of the way. The other 50% to really get results that look good and reasonable and match existing techniques for the cases where we have solutions. I should say, of course, the obvious, like the Eulerian method that I showed you is not an option for anything in dimension 4 or bigger. Because even in 2D, we had about 3 million degrees of freedom. Guess what happens in 3D 4D, 10D, 100D. It's not an option. So you have to face it. Even if you like these 0.5% improvement, you're not going to get that for the problems you care about. You can get there with a neural network. For us, it meant we had to go through all the math. There were lots of change of variables, calculus things, and screwing any of these things up broke our neck multiple times. But finally, we made it, and you can do it then. And yeah, the open issues. I mean, there are plenty of open issues right now. Smoothing some things under the hood, like the optimization or implementation, is one. But I think one crucial thing is now to apply it to actually more meaningful problems and to look for data sets and applications to do this. And yeah, with that, well, thank you one more time, and happy to answer all questions now or later.